Hello everybody. We're back to work on finishing off chapter 15. And today what we're going to do is we're going to let our calculators cool off a bit. And we are going to be looking at how we manipulate a reaction to try to control the amount of product. Okay? Last semester, we concentrated in on limiting reagents to control the amount of product. So remember, a limiting reagent is the reactant that we purposely supply in a smaller amount so that it limits the amount of product. By using a limiting reagent, we're essentially never letting the system to come to equilibrium. And if it never comes to equilibrium, then we don't have to worry about backwards and forward reactions. Only the forward reaction is happening. We never reach equilibrium, and we control the amount of product. Okay? So, let's scroll down here. So one of the ways that we can control the amount of product is by limiting reagent. So, let's say we don't have a limiting reagent situation. How do we control or manipulate the amount of product then? Okay? Well, we can manipulate a system that is at equilibrium. We can disturb it, okay, knock it out of balance, so to speak, so it goes to reestablishing an equilibrium. And when we do this disturbance of the system and it comes back to a new equilibrium, we're going to change the amount of product that is produced. Now, it will not be, remember when we knock a system out of equilibrium and we disturb it, it's going to come to a new equilibrium point. It's not going to come to the exact same equilibrium point it has before. Okay? So our emphasis for today is Le Chatelier's principle. And guys, this is not a one-off look at this. We're going to mention Le Chatelier's principle for the rest of the semester. So we need to understand Le Chatelier's principle. Yes, Le Chatelier's principle says when a chemical system at equilibrium is disturbed, it reattains equilibrium by undergoing a net reaction that reduces the effect of the disturbance. Okay? So we have a system in balance, and we disturb it. It moves back to a balance point. So we're going to look at how we disturb a system and then how the system responds to each one of these disturbances. Okay, we can disturb a system by either adding a reactant or product. We can remove a reactant or product. We can change the total pressure in the system by changing the volume of the container for a gaseous reaction. Okay? When we change the volume of the container, we change the partial pressures of every substance in there. That means we're changing the concentration of every gaseous substance in the chamber. And then last but not least, we can change the temperature. So we're going to look at a system, and then we're going to make disturbances. Okay, so here we have the reaction phosphorus trichloride plus chlorine going to phosphorus pentachloride, everything in the gas phase. If this system is at equilibrium and we were to add in PCl3, the phosphorus trichloride, if we add in the phosphorus trichloride, we now have too much reactant compared to product. In our equilibrium expression, the denominator is too big. So if I've added in reactant, and I have too much reactant compared to product, this system is going to want to run in the forward direction to get back to an equilibrium position. Okay? So we disturb the system, and it's going to run in the forward direction to eliminate the problem. So we add a reactant, it's going to run toward the opposite side. This is called a shift toward product. So concentrations for reactants would go down from the disturbed position, and the concentration of products would go up. What do you think if we added in a product? We dumped in some PCl5. Well, if I add in reactant and it shifts or runs toward product, if I add in a product, we're going to see a shift back toward reactant. So we're going to see a decrease in product from the disturbed position and an increase in reactants. So anytime we add something into a reaction vessel, it's always going to shift toward the opposite side. So if I add in a reactant, we cause a shift toward product. If I add in a product, we cause a shift toward reactant. Okay? Now, let's look at removing something. Our second type of disturbance. If I remove product, what do you think that would do? If I remove product, okay, that means I have reduced the numerator. So I have too much reactant compared to the amount of product. That means we're going to cause a shift toward product. The reaction is going to run in the forward direction from the disturbed position to reattain our new equilibrium. So by the same token, if I were to remove reactant, I would cause a shift toward reactant. So when we add things, we cause a shift toward the opposite side. When we remove things, we cause a shift toward the side where we remove the material. Okay? So we're going to look at a nice little problem out of the book. We're going to look at problem 15.14. Okay, let me shift you over here, guys, so we can get a look at the board. Now, 15.14 has the following reaction. 2 BrNOs, gas, decompose into 2 nitrogen monoxide gases plus a bromine molecule in the gas phase. Okay? Now, we're asked if we add Br2, what happens? And then we are asked what happens if we add BrNO. Okay, so let's look at these two. Well, bromine is product. So when I add bromine in its product, we're going to cause a shift toward reactant. So it runs in reverse. When I add BrNO, bromine mononitrogen monoxide, what a name, it's going to run in the forward direction. So it shifts toward product. So it runs in the forward direction. Okay? So we always cause a shift toward the opposite side. Now looking at this same reaction, okay, because we might as well get double duty out of it. What would happen if I remove nitrogen monoxide. Well, I have something, a second reaction or some kind of absorber that specifically absorbs that material. If I remove nitrogen monoxide, then we're going to cause a shift toward product. So it runs in the forward direction. Okay? So those are the first two types of disturbances. Now we're going to look at changing pressure. Okay? So let's think about changing pressure. Now, thinking about changing pressure, we want to distinguish between changing a partial pressure and between changing the pressure through changing the volume of the container. When we change the partial pressure, it's just the same as changing a single concentration. So we treat it like the first two cases we've looked at, adding something or removing something. When I talk about changing total pressure, totally different ballgame. Okay? When we're changing the total pressure of the system, we're going to do it by changing the volume of the system. Okay? If we decrease the volume of the system, we increase the total pressure, which means we've increased the concentration of all the gas components. If we increase the volume, we decrease the total pressure and we decrease the concentration of all of the reactants. Okay, so the shift we're going to make is based on the difference in the moles of gaseous molecule from one side of the reaction to the other. If you increase the total pressure by decreasing the volume, then the reaction shifts to the side with fewer gas molecules. When you decrease the total pressure, you've done that by increasing the volume, and the reaction shifts toward the side with more gas molecules. Okay? So we're going to look at problem 15.15 in the book. Okay. Get the board erased here, and then we'll go for problem 15. All right, let's shift over. Now, if we look at problem 15 here, we've gotten the reaction 2 sulfur dioxide gas plus an oxygen gas going to 2 sulfur trioxides in the gas. Okay? Now, let's think about decreasing the volume. Well, we know that total pressure goes up. Okay? So if the total pressure goes up, we want to shift toward the side with fewer gas molecules. So I'm going to shift to the side with fewer gas molecules. So in this case, the reactant side has 3 gas molecules. product side has 2 gas molecules. So we see a shift toward product. It's going to want to shift to the side with the fewer gas molecules. If we were to increase the volume, it would cause a shift back toward reactants. Okay? Now, let me show you, let's see. If the number of gas molecules is the same on both sides, then increasing the volume or decreasing the volume isn't going to have any effect on the equilibrium. Okay? The other thing to remember is that if you add in an inert gas is one like argon, neon, something that's not going to be reactive, not participate in the reaction, it's not going to affect the equilibrium either. If you add in a solid, remember they don't appear in the equilibrium expression, they're not going to affect anything. So, pressure effects. The last effect for us to look at is the temperature effect. Okay? The temperature effect is going to depend on whether the reaction is endothermic or exothermic, and changing the temperature actually changes the value of the equilibrium constant. Okay? For an exothermic reaction, heat is a product. In an endothermic reaction, heat is a reactant. They're invisible reactants and products, but they're there. For exothermic reactions, as we increase temperature, we add in thermal energy, which changes the total energy content of the system. So we're adding in a product, we cause a shift toward reactants. So for exothermic reactions, increasing the temperature causes the reaction to run in reverse. If we want to get more product for an exothermic reaction, we actually have to lower the temperature so that we cause it to run in the forward direction. For endothermic reactions, heat is a reactant. So when we increase the temperature, we cause a shift toward product. If we wanted to decrease product, we would want to lower the temperature. So endothermic, it's a reactant. Exothermic, it's a product. Okay? Now, if it's exothermic and we cause a shift toward reactants, that means that, and we increase the temperature, cause a shift toward reactants, that means that we're going to decrease the value of the equilibrium constant. At lower temperatures for an exothermic reaction, you're going to see an increase in the value of the equilibrium constant. We're doing the exact opposite for an endothermic reaction. When we increase temperature, we cause a shift toward product, we increase the value of K, the equilibrium constant. If we were to decrease the temperature, we would decrease the value of the equilibrium constant. Okay? So let's look at practice problem 15.16. All right, let's shift over here. Okay, if we look at 15.16, we've got that reaction 2 sulfur dioxides gas plus oxygen in the gas phase going to 2 sulfur trioxides gas. So, if we look at this reaction we are told is exothermic. So that means that heat is a product. Okay? So if I increase temperature, I'm adding in heat, it's going to run to the opposite direction. We're going to cause a shift toward reactant. Okay, so it runs in reverse. Now, if it runs in reverse, that means the value of K goes down. If I wanted the value of K to go up and to get more product, I would have to lower the temperature. All right? Now we're going to look at a couple of problems at the end of the chapter just to make sure that we're good at this. We're going to look at problem 72. End of chapter. Okay, in problem 72, we've got the reaction carbon solid plus water in the gas phase gives us carbon monoxide gas and hydrogen gas. Okay, so let's look at taking this system and doing some disturbances. Oh, we're also told that this reaction is endothermic. That means that heat is a reactant. Okay? So when we look at this, want to know what happens if we add carbon? The answer is nothing. Carbon is a solid. I add more solid in, it doesn't change the concentration any at all. Okay? So let's add water in the gas phase. Well, water is a reactant, so we're going to see a shift toward product. Okay? Now, let's increase the temperature. Well, if I increase the temperature, I'm adding in heat, which is a reactant. We're going to cause a shift toward product. The value of K goes up. Okay? Now, let's increase the volume of the container. If we increase the volume of the container, we want to shift to the side that has more gas molecules. On the reactant side, there's 1. On the product side, there's 2. So we're going to cause a shift toward product. Okay? And if we add in a catalyst, okay? Then there's no change. A catalyst gets us to equilibrium faster. It never changes the equilibrium position. And then we add in an inert gas. Again, no change. Okay, so that's Le Chatelier's principle, and that is the end of chapter 15. So you've got everything for 15. We'll move on to chapter 16 in the next lecture.